Yeah, good day and welcome to this video on matrix algebra. It's from Unit 3 Specialist Mathematics and the topic vectors and matrices. So in this one we'll be covering the Cambridge work from 7A and 7B, which really is just revision work anyway. So I'll be talking through some revision to help you prepare for these stuff later in the chapter. So there's a few things you need to recall to be successful in this, and I'd encourage you to have a read through your textbook and just make sure you're over and understand this information. You don't have to know it all before you do the exercise. Obviously, the main feature and purpose of the exercise is to help you to recall this information. So a matrix is a storage array of data, and a vector is a special type of matrix, and it also has some special properties or is defined slightly differently in some context. A matrix has dimensions, and we list those dimensions from the number of rows by the number of columns, and that is that vertical number 3. So I'm now looking at this, and then that 2. So it's a 3 by 2 matrix. And we also give the cells references as well. This is cell A21 because it's in the second row but the first column. So the rows are listed first, as I've mentioned there. We add or subtract by adding or subtracting cells. So this is pretty easy. Just add or subtract those matrices as you'd expect. Keep in mind though, this is very restricting. It means that to add and subtract matrices, you really have to have exactly the same dimensions. It's not possible just to add what's available. If they're not the same dimensions, you can't add them. It doesn't make sense within pretty much all the contexts that we use matrices for you to add them. We multiply matrices a little bit differently, and I am just going to briefly talk through this here, but if it's something you're not sure about, well, I'd probably go back and have a closer look at this. And basically, we multiply matrices by, as you can see there, by doing the yellow times the yellow, so the first row multiplied by the first column to give us cell 1, 1 in our result matrix. And the 1, 1 represents first row, first column. So we do A11 or A11 times B11 and then A12 times B21. And that gives us our first cell in the results matrix. I've done the same with the green one there, but obviously there's two others as well. So I would really strongly suggest you pause the video now and just have a look through and make sure that it makes sense. That, for example, this value here, that has come from the second column but the first row. So I've done a multiplication of first row by second column. So that is first row by second column. I've messed up all my colouring now, but hopefully you can see where that's come from. Just check it makes sense. We have some special matrices. First one is an identity matrix, and an identity matrix is a square matrix with leading columns of 1s. So 1, 0, 0, 1, or 1, 0, 0, 0, 1, 0, 0, 0, 1, all the way down 4 by 4, 5 by 5, 6 by 6. And then we also have some matrix algebra. So an inverse of A takes A back to the identity. Just like you would have an inverse of a real number under the operation multiplication, the inverse of 2 would be a half, because 2 times a half takes us back to 1, and 1 is the identity under multiplication. And there's a few other examples floating around out there. But again, you've learnt this previously, so hopefully you recall it. And we also defined a determinant. And the determinant of A helps us to generate an inverse. So the inverse can be quite tricky to work out. There is a way of doing it algebraically, but the determinant actually comes from generalizing the algebraic one. So that would be, try and find the inverse of the matrix A, B, C, D, and we come out with this special determinant. And in fact, the inverse of the matrix A, B, C, D here is this matrix here, A inverse. And that is 1 over the determinant of A, which is AD minus BC, multiplied by D minus B minus C and A. Now I'd take some time now before we move on to talk about some of the specific tools and concepts behind matrices, to just go and check out the formula sheet as well and make sure you're aware of what is and isn't on there and where to find it, because familiarity with the formula sheet really helps in exams. Okay, so let's have a look at these linear transformations. Geometric application of the proof can come back, but I'm not going to talk about it too much here. So I'd suggest you have a look at that again if you want to. And in addition to work from last year, which is the linear transformations work, it is name dropped in Unit 3 and therefore it is now available as an external exam topic. So remember, we have defined an original vector, xy, can be transformed by a matrix, so there's your linear transformation A, B, C, D, to get an image vector, x dash, y dash. Now, of course, x, y is a 2 by 1, and therefore the matrix has to be a something by 2. And most of our linear transformations, the common ones, are 2 by 2s. But we also were able to add 2 by 1s, add other vectors, and they were translations. So there's a couple of special cases, but here are the ones that you might recall from last year. And again, it's worth noting what is on a formula sheet, what is easy to remember, which bits you can put together. They're all fairly simple, so these are all individual cases. So you can see here reflections work just by negating either the x or the y, and then you've got the reflections over the diagonal line work just by flipping the ones to the other diagonal. And so you've got all these little things. They're very basic changes. Additionally, remember that the multiplication AB applies B and then A. So if we had two transformations and they were B and A, but we wanted to do B first, we would have our original X, we would multiply it by B first and then A. Looks like it's in the other direction though. And we would be allowed to calculate AB first to get a combined transformation and then multiply it by X, and that would work in exactly the same way. A inverse reverses A. That's what an inverse is. And also remember this little tidbit here, which is snuck into a couple of exams that I've seen. The determinant of B times the area of the shape is the area of the image after a B transformation. So if you have a transformational matrix and you're multiplying it by an X, an original, that actually defines a shape, say a square. So 1 by 1 square, and the determinant of B is 4. Then this new shape, which might or might not be a square, will have an area of 4. And here we've suggested that we complete some exercises 7a and 7b. So if I just scoot back up to the top, you'll see I've just said 7a, 7b, your selection. I suggest that you spend just a bit of time floating through those and make sure that everything you come across you understand and you know. And obviously for all of you that will require a different amount of time. All the best.